So we're going to pick up where we left off in the last video. So in the last video, we had written our law of mass action. So now we're going to plug in our information. Hopefully you've taken the time to do that. I'm going to pick up here. So you got the concentration of NO2. We're going to plug that in here as 0.0040 molar, and that's raised to the fourth power. And then we're going to plug in the concentration of the ammonia, 0.031 molar. And that's raised also to the fourth power. And then concentration of oxygen, which is 0.26 molar, and that's raised to the seventh power. All right, so let's plug this in. When you take 0.0040 and raise it to the fourth power, and again, we do not have to worry about our units here in this calculation, so don't stress out over the units, but this would be to the fourth power, but K is a unitless number. For that part, I get 2.56, which would be 2.6 times 10 to the negative 10. And then 0.031 raised to the fourth power gives me 9.2 times 10 to the negative 7. And that was to 2 sig figs. And then 0.26 raised to the seventh power gives me to 2 sig figs 8.0 times 10 to the negative fifth power. So for the final K value, we're going to round that to 2 sig figs, and I end up getting 3.5 for that answer. Let me double check that just to make sure. Yes, that's what I got, 3.5. That's your K value. All right, that would be your equilibrium constant. So let's take a look at this one. We're going to talk about how to use the law of mass action to write the equilibrium expression, and then solve again for K on this one. So we want to write our equilibrium expression. These are all gases, so you could write it in terms of concentration, or you can write it in terms of pressures. It just really depends on your data here. If you write it in terms of concentrations, you'll get K is equal to the concentration of the NO squared, because you do products over reactants, so the products always go in the numerator, squared because of the 2, times the oxygen concentration to the first power, because this is understood 1 here, divided by concentration of NO2 squared, again, because that's your coefficient. Now, some applications of the equilibrium expressions, some little shortcuts, if you will. If you have a given reaction that you wrote the equilibrium expression for, like the one we just did in the last slide, for the reaction, if it were written in the reverse, then its equilibrium expression would just be the reciprocal of the original equation. So if you take a look at this particular one that we just used, this was what we call the original, which is one we just did on the last slide. Notice you have your NO2 as a reactant here and the 2 products. So this is what we got for our law of mass action. Well, if we reverse this reaction, so we're just flipping the reaction around, compare this reaction to this one. This flipped it around, so our products and our reactants are on opposite sides. So that means this would be flipped. So what we have here is a situation where if you recognize that the reaction is just the reverse, instead of recalculating your K, you can just understand that K, we'll call this K of the new reaction, we'll call it K prime, is equal to the 1 over the original K. this being our original k, the inverse of it. So it's k prime would be equal to the original k to the -1 power. So I'll put k original, okay, and this being k original. Now some other things. If the balanced equation for the reaction happens to be multiplied by some factor n, then the equilibrium expression for the new reaction would be the original expression raised to the nth power. So going back to that same example we looked at a few minutes ago, this being the original, okay? If I compare this new reaction to the original, what we've done is taken the same reaction, but they've basically multiplied by 1/2 or divided by 2. And I know this is not normally how we would see this, but just kind of to show you the point about what you would do if you see a related reaction. And all they've done is they've multiplied the new reaction by some integer. So that means k prime, or the new k, will be equal to the original k raised to the power that it was multiplied by here. This had been multiplied by 1/2. This has been multiplied by 1/2 to get this new reaction. So you just take your k, original k, and raise it to the 1/2 power. So like if this had been multiplied by 2, you would have taken your original k and multiplied it by 2, or raised it to the second power, excuse me, you square it. If this has been multiplied by 3, you would take your k and cube it. Again, these are just shortcuts. So let's take a look here at this. For the reaction N2 plus O2 is in equilibrium with NO, if we're told that the K for this is 4.1 times 10 to the -4, and want to apply the things we just talked about, let's compare for the new reaction. If we compare this reaction to the original, all they've done is multiplied the original by 2. So that means K prime, or the new K, is equal to the original K squared. Instead of having to recalculate and replug in, we just take our original K, 4.1 times 10 to the -4, and you square it. And so that's going to give us, for our K prime, 1.7 times 10 to the -7. All right, so let's look at example B. So here, if we compare this reaction to the original, all we've done is reversed the reaction. So K prime is going to be equal to the original K flipped. So 1 over K, or K to the -1 power. So let's take our original K, 4.1 times 10 to the -4, and raise it to the -1 power. So we're going to need 2 sig figs. So that means our new K prime is equal to 2400. And finally, let's look at the third example. If you compare C to the original, always compare to the original, they've flipped it. Notice the NO is a reactant here, where it was a product originally, and these were originally our reactants, now they're products. So they flipped it, and they've multiplied it by what? By 2. So that means for our new K prime, we're going to do both. We're going to take 1 over the original K, and then we're going to raise it to the second power. Now remember, we've already done the 1 over the original K here, 2400, and so we just need to take that and square it. So that means the new K, K prime, is going to be equal to 5.9 times 10 to the 1, 2, 3, 4, 5, 6 power.